Hi, my name is Eric. Today I'll be doing 4.4, 5, 6, 7, 8. And then the other guy is going to do 4.3 and then 4.44. So let's see here. Let me just pull this up. So number 5 is Alice chose primes, PQ, and an exponent. Determine her public modulus and private exponent for RSA. If she receives the following messages, determine the plain text that she obtains. So we got our stuff here. Modulus is P times Q. Get this number right here. Your n value is just minus 1 for each and then multiply them to get this value. Here's your exponent. Your private exponent, or the d value, I'll just call it the d value from now on, is just the inverse of your exponent. Modded by the n value we got earlier. I hate doing things by hand, so a lot of this I have like little Python stuff things for. So you could do Euclidean's algorithm, all that jazz. That sounds like fun. Go ahead and do that if you want. But I just have this inverse mod.py. You just plug in your values here. You hit run. Bada bing, bada boom. 14,225. To decrypt, it's just your ciphertext to the power of your d variable modded by the m variable that we got earlier, or your modulus. And so for this, you could do, what you learned in 4.3. And if you want to fill out a bunch of paperwork and kill a bunch of trees, go right ahead. But I've got this little thing called palmod.py. Makes my life super easy. Saved half the rainforest making this. So 13,667 to the power of 14,225. Modded by 17,741. You plug all those in here. You hit run. Here's your value, and that's the plain text. You do the same thing for down here. You hit run, you'll get this value. Moving on. Number 6, use the modulus in exercise 4 to encipher the following message in block mode. Using 3-letter blocks, write the resulting numbers down as 5 decimal digit numbers. Block size is 3, the exponent is 7. The modulus is 22,987. You'll get that from number 4. To encipher something, you just take your plain text to the power of e, modded by m. And again, use power mod.py. But first we got to split this up. So 3-letter blocks: TAK, EAH, IKE. Then just, I always do this because it's easy for me to keep track. Alpha through Z, 0 through 25. T is 19. T is 19. A is 0. K is 10. And you do that for all 3 sets. Then to get a number we can throw into our little equation up here. Since it's a 3-letter, you just do 26 to the power of 2 times, the number value of this letter, plus 26 to the power of the number value of the next letter, plus, which is 26 to the 0, but that's 1, so you don't really need to write that out. Just the number value of the next letter, so 10. So 26 squared times 19 plus 26 times 0 plus 10 gets you this number right here. You do that for all 3 right here. Then you have to actually encipher it. So to encipher TAK, you take this number up here to the power of 7, modded by the modulus, this m value. And again, I just power.mod or palmod.py. You plug it in, you get 6712, but it says it wants 5 letters. So in the book example, they just slap a 0 in front of everything. So I just did that here. So if I got 6,712, I would transmit that, but I'd slap a 0 in front of it. So you gotta do that for all three of these. So that's enciphering, and then you got decipher. So for the next one, so it says use modulus in exercise 5 to decipher the following message, which was enciphered in block mode with encryption. Exponent S is 12,707. Assume that each block of 5 decimal digits represents a block of 3 letters. So ignore PT. This is supposed to be ciphertext. This is what we got. So it's 369. So 18 letters total. It's a 3-letter block size. So we're going to do the 26 to the power of 2 times x1 plus 26 to the power of 1 x squared plus x3. So the modulus from number 5 is 17,741. The n value is also the same, so 17,472. We've got a new exponent power of 12,707. So to get the new d value, you have to do the inverse mod of that times the n value, or mod n value. I did the inverse mod.pi again. I got 11. So you can see that right here. So then to decipher the first block, it's the 13,681 to the power of 11 modded by 17,741. You bleep bloop bleep into palmod.pi. You get 2,405. Then again, it's, how many times can I fit 26 to the power of 2 into 2,405? Turns out it's 3. So 26 to the squared times 3. And then you subtract that from 2,405. I'm left with 377. How many times can I stuff 26 into 377? Turns out it's 14 times. You're not going to get these numbers exact, obviously, so to the floor. So, like, for example, I don't know what it is exactly off the top of my head, but if it's like, 14.663, right? You just go down to 14. So you multiply this together. It's 364. 377 minus 364 is 13. So my first 3 letters are 3, 14, 13. So 3, 14, 13, DON. Sorry about that. So DON right here. You do that again and again and again and again. You get don't worry, be happy. And then the last one's going to have 2 padding letters, so XX. And again, just make your life easy. Use powermod.pi. Or you can do it by hand. More power to you if you want to do that. But I hate math, so here we are. The number 8 is the following message was enciphered by RSA of a 5-letter message using the modulus M, really big number, and the exponent S, really big number. The ciphertext, or Y, is like really big number. Perform cryptanalysis to break the cipher and obtain a message. So I have M. I know that M is 2 prime numbers that are relatively prime to each other. I have this from a homework assignment or 2 ago that we had to do. All you got to do is you fill out the number. It'll return false if there's no 2 relatively prime numbers that will multiply to each other. In this case, there is, obviously, because they want you to figure out what it is. So I got 1,741 and 1,741, and 6,827. So those are my P and Q values. Now I have P and Q values. I can find N by subtracting 1 from each and multiplying it to get a really big number. Now that I have N, I can get D because I have E. So the inverse of E modulus my N value, again, inverse mod.pi, I get 13. So now that I have that, I can decipher. So decipher the ciphertext. I take my ciphertext, the power of 13, modded by my modulus, it's a really big number. Again, just use poundmod.py, make your life easy. I get this number right here. So then it's just a game of, I've got 5 characters, so 26 to the 4th, 26 to the 3rd, 26 to the 2nd, 26 to the 1st, and then 26 to 0 or 1. So now it's just how many times can 26 to the 4 to the 4th fit into here. Turns out it's 2. Subtract these 2 from each other, I get this. How many times can I stuff 26 to the 3rd in there? Turns out it's 11. Subtract these 2, get this number right here, 26 squared. How many times can I stuff 26 squared into here? Turns out it's 4. Subtract, how many times can I stuff 26 into 17? I can't. So it's 0 and 17. So 2 is C, 11 is L, 4 is E, 0 is A, 17 is R. And that's all she wrote. So I'll post this, my video, and I'll post the poundmod.py, primer.py, inversemod.py, and then you can use those to I'm not like the best at coding, so you could probably make this a whole lot better and interactive. I'm just lazy, so I just fill out the variables here and I hit run every time, but I'm sure you could do something else. Alright, the other guy's gonna do the other half, so good luck. Happy holidays.